In Chapter 9, Section 11, we want to look at how we convert alcohols into alkyl halides. Sometimes that is a reaction that we will be interested in doing. So since that is a reaction that we're interested in doing, let's figure out how that works. Now, we can't use the alcohols directly and do substitution with those because hydroxide is not a good leaving group. Recall, the stronger the base is, the worse something is as a leaving group. Since hydroxide is a strong base, it's a lousy leaving group. So, that reaction just won't occur. Instead, we can add a strong acid to it, like HCl, HBr, or HI, and that will convert it into a good leaving group. It'll convert the alcohol into an H2O plus group, which will leave as H2O, and that will give us our alkyl halide. So that reaction occurs quite easily. All right, and it works with primary, secondary, and tertiary. Let's look at a couple of examples, and I'll show you one that's primary and one that's tertiary. So it works with a wide variety of things here. So here with the primary, here we've got the alcohol, and we can convert that alcohol into the bromide using HBr. And with the tertiary alcohol, we can convert it into the chloride using HCl. We'll find that this reaction goes faster as you have a more substituted alcohol. So the reaction goes faster as we have a more substituted alcohol. All right, so let's look at number 48 on the in-class assignment. This one is pretty straightforward. We'll switch over to our document camera here. So we want to draw the organic product when 1-methyl cyclohexanol is treated with each reagent. And so here our reagent, our starting material, is the 1-methyl cyclohexanol. So if we use sodium hydride, we saw this a little bit earlier, this will deprotonate that OH to make the alkoxide. So we'll have O minus. I'll go ahead and put the counter ion, sodium, because it will be a sodium alkoxide. And since hydrogen ended up with hydrogen, we're going to have H2 as our byproduct. All right, if we just throw in sodium chloride with this, we're going to get these two things just mixed together. We will not get a reaction. So this will give us no reaction. And again, the reason for this is that OH minus is a really bad leaving group, so no reaction will occur. With HBr, we'll get substitution and convert that into a bromide. All right, so we'll get that as a bromide, and in case you're curious, our byproduct here would be H2O. For HCl, we can get a similar kind of reaction to occur. We'll get that chloride, and again, plus H2O. Sulfuric acid, as we saw in a previous section, we'll convert it into alkenes. And so, again, with this alcohol, our alkenes, we'll get this one, and this one. And then we'll also get plus H2O. As far as which one would be our major product, of course, it'd be the more substituted alkene. So this would be our major product. All right, now for this one, we've got sodium bicarbonate. Well, this acts as both an acid and a base, but it's not a strong enough acid to react with the OH, and it's not a strong enough base to deprotonate the OH, so this is going to give us no reaction. Okay. On this one, we're going to form the alkoxide in the first step. So we'll form this in that first step with sodium hydride, and then that will react with this alkyl halide, the primary alkyl halide, and we will get an ether. So we will get that ether. And then I'll put plus H2O, or plus H2 because of the hydride, and plus sodium bromide. There we go, sodium bromide. So there is our ether. I don't think that was on screen there for a minute, but there it is. All right, and then finally with the Tosylate and pyridine, this is a dehydrating agent. So we'll get the same products that we got here. And we'll get the same one as a major product as well. All right, so that is number 48. So let's go back and we'll find that our mechanism will depend on the structure of the alcohol. So, and we'll also find that the rate depends on the mechanism, and the mechanism depends on how the substituted the alcohol is. So here, if we always protonate as our first step, we create the good leaving group, but whether this happens as an SN1 where we form a carbocation, or as an SN2 where we get simultaneous breaking of the carbon oxygen with making of the carbon halogen bond, that depends on what kind of alkyl groups we have here. If it is methyl or primary, it's going to go by an SN2 mechanism. If it is secondary or tertiary, it will go by an SN1 mechanism. All right, so the more substituted, the more likely it is to go by SN1. The less substituted, the more likely it is to go by SN2. For the methyl and the primary, that SN2 mechanism, first step is we protonate the OH and form a good leaving group. So we'll form H2O as a leaving group. Then the nucleophile comes in and reacts with the carbon, and in this case it reacts with that primary carbon, reacts with the carbon and will break the bond between carbon and oxygen while simultaneously making the bond between carbon and bromine in this case. The secondary and tertiary are both going to go by an SN1 mechanism. So in the SN1 mechanism, again, we protonate because that's always our first step when we're dealing with these alcohols. We'll protonate. And then in a second step, and this will be our rate determining slow step, is going to be to break the bond between carbon and oxygen with H2O as a leaving group, and we'll form the carbocation. And then in a third, fairly quick step, the halogen, in this case bromine, will come in and react with that carbocation, and that will give us the reaction. All right, so the reactivity of the acids, we'll find that the stronger the acid is, the faster the reaction goes. So HI will go faster than HBr, which goes faster than HCl. And HF will not work at all. So don't even try HF. Besides, HF, really dangerous. We'll find that the strength of the nucleophile with chloride is just not that good. All right, so if we're going to do the primary, of course, primary has to go by a SN2 mechanism. And the chloride is just not as good of a nucleophile as the bromide and the iodide. So it just doesn't work as great as a nucleophile. So we need to add a Lewis acid as a catalyst that will help the reaction. Technically, it's not really a catalyst because it gets used up in the course of the reaction. And catalysts, by definition, don't get used up. But we need to add something in there as a Lewis acid to help the reaction along. So the zinc chloride will complex the oxygen, and when it complexes that oxygen, then the chloride can come in and react with the carbon in that SN2 reaction. It just makes this a better leaving group. All right, and then the stereochemistry, of course, will depend on the mechanism. If we've got an SN2 mechanism, which the primary alcohol goes by SN2 mechanism, then we will get an inversion product. All right. The tertiary alcohol, also the secondary alcohol, will go by an SN1 mechanism, and with that we will get a racemic mixture. All right. So for this, we want to look at number 52, but just parts A and B. And that's because C and D are part of the next section, but I didn't want to go all the way to the end of that next section without having done these. So we'll switch over to our document camera again. And so here we've got a secondary alcohol and HBr. Since it is a secondary alcohol, that means that the mechanism for this is going to be an SN1 mechanism. So since we have a secondary alcohol and we're using HBr, this is going to be an SN1 mechanism. Since it's SN1, we get a carbocation intermediate, and that means that that stereogenic center is not going to be retained. We're going to get racemization of our product. So 1, 2, 3, 4, 5, 6. All right, so one of our products will be where we have the bromide coming forward, hydrogen going back, and then our other product where we'll have the hydrogen coming forward and the bromide going back. All right, on part B, we've got a primary alcohol, and we're using HCl and the zinc chloride, and again, we need that zinc chloride to make this reaction work. The primary doesn't work that well, the SN2 doesn't work that well unless we have that zinc chloride in there. So we're going to do the SN2 mechanism. And with the SN2 mechanism, that means that we will get inversion of that stereochemistry. 1, 2. So we have 5 carbons. And then here is the OH. And since we're getting inversion, I'm going to switch these two. So we'll get deuterium there and hydrogen there. All right. So that will be our primary product on that. Let's go back and look at the next thing. So we want to convert the alcohol into the alkyl halide, but sometimes we just don't want to use HCl or HBr, and so we can pick a different option, and the different option is only available to primary and secondary alcohols, but we can use thionyl chloride and phosphorus tribromide as options. The thionyl chloride will convert your primary and secondary alcohols into alkyl chlorides, and of course the phosphorus tribromide will convert the alcohols into alkyl bromides. These reagents, they convert the OH to a better leaving group, kind of like when we protonate it, converts it into H2O, which is a better leaving group. Well, here we're going to convert it into a different better leaving group. And we can do this with HCl, or we can do this with chloride and bromide. You'll notice that we don't have an option for iodide. The bonds with iodide just aren't strong enough. The math doesn't work out for it. So we can't do this with iodide. Although there are some tricks we can do, but we can't do this with the iodide. All right, so converting the alcohol into an alkyl chloride with thionyl chloride. We'll take the primary and secondary alcohols and we'll treat them with the thionyl chloride and pyridine. And pyridine is important here. And it forms an alkyl chloride with HCl and SO2 as our byproducts. So here's a primary, there's a secondary. Notice we can't do tertiary. And what that tells us is because it's primary and secondary and not tertiary, that tells us this probably is a particular type of mechanism. Why don't you pause the video for a second and see if you can figure out what kind of mechanism it is. All right, now that you pause the video, hopefully you said that must be an SN2 mechanism. If it only works with primary and secondary, but not with tertiary, it must be SN2, and that would be correct. So it is an SN2 mechanism. We're going to look at the whole mechanism here. All right. So for this mechanism, the alcohol is going to react with the thionyl chloride. When it does, the chloride will be lost as a leaving group. We will have this. All right. So react with the thionyl chloride. We will have this. Once we have this, we're going to deprotonate that with our pyridine, and that will give us this. This is a good leaving group. And so our chloride will come in and react. Will come in and react with the carbon, again, primary or secondary, and that will give us the alkyl chloride plus sulfur dioxide plus chloride. All right, and that is that's a very convenient. A very convenient reaction to be able to do. So SN2 attack of the chloride and simultaneous loss of the leaving group. One nice thing is the SO2, that is a gas, so that just bubbles right off. So this is a pretty cool reaction. The downside of this reaction is it's kind of stinky, so you need to do it in a hood. In a similar fashion, we'll find that we can convert alcohols into alkyl bromides using PBr3. Again, it only works with primary and secondary alcohols, which hints to us that this must be an SN2 mechanism. So here's a primary and a secondary alcohol. We treat it with PBr3, the phosphorus tribromide, and we will get these alkyl bromides and this as our leaving group, as our byproduct. So again, it is an SN2 mechanism. So the conversion of the alcohol to an alkyl bromide, it does go by an SN2 mechanism. The first step is going to be the reaction between the alcohol and the phosphorus tribromide. We're going to lose bromide in the course of that, and we'll form a new bond between the oxygen and the phosphorus. And then bromide is going to come around and react with, it will come around and react with the carbon, again, either primary or secondary carbon. And we'll get loss of this leaving group, which is the HOPBr2. All right. Turns out phosphorus really loves making bonds with oxygen. So forming oxygen-phosphorus bonds is a very favorable thing to do. All right, and then here we've got SN2 attack on the of the bromide. That's this step, right? That's this step. All right, here is a summary of all the different ways that we've learned so far to convert alcohols into alkyl halides. For chloride, we can do HCl or thionyl chloride. HCl works with all primary, secondary, and tertiary, but it goes faster with the more substituted. The thionyl chloride reacts with primary and methyl and has to go by primary methyl and secondary, but has to go by an SN2 mechanism. So tertiary is off the table for thionyl chloride. For bromide, we can use HBr, again, all three, so primary, secondary, tertiary are all available, and the methyl, if you want to do by SN2 mechanism. For PBr3, only by an SN2 mechanism, which means methyl, primary, and secondary only. We can't do the tertiary with this. For iodine, we only have HI as an option. We do not have one that's analogous to the thionyl chloride or the phosphorus tribromide. We don't have some weird iodide compound that will work with that. Again, the bond energies just don't work for it. So we're pretty much stuck with HI. All right, and we're going to combine that with one other topic here, which is looking at tosylates. So tosylates as leaving groups. All right, so alcohols can be converted into alkyl tosylates, and a tosylate is that's short for para-toluene sulfonate, and that ends up being a really good leaving group. So we can convert an alcohol into a tosylate. A tosyl group is abbreviated TS, so alkyl tosylate is ROTS. All right, so this is tosyl and this is tosylate, right? If you've got the alkyl oxygen and then the tosyl group, that's a tosylate. So tosyl and tosylate. All right. So the way that we prepare alkyl tosylates is that we take the alcohol and we react it with para-toluene sulfonyl chloride, and we have to do it in the presence of pyridine. So we have to do it in the presence of pyridine. So the alcohol reacts with the para-toluene sulfonyl chloride, or the tosyl chloride as the short way of saying it, and pyridine as a reagent to soak up H+, and we will end up with the tosylate, and that tosylate ends up being a good leaving group. The reason that tosylate is a good leaving group is that the conjugate acid of tosylate is toluene sulfonic acid, and we know from earlier that the pKa of toluene sulfonic acid is -7. It is a strong acid. So the pKa of para-toluene sulfonic acid is a strong acid. All right, so now for stereochemistry considerations. If we're going to, when we pay attention to the stereochemistry, one thing is really interesting when we're preparing a tosylate from a chiral alcohol, the configuration of the stereogenic center is retained. So for example, here we've got this S-butanol. So this is a stereogenic center, and because the carbon-oxygen bond is never broken in the course of making this, that stereogenic center is unchanged. So we just make a new bond between the oxygen and sulfur, break the bond between chlorine, between the chloride and the sulfur, and we'll get this. The pyridine comes in and deprotonates and gives us our tosylate, and you'll see that the stereochemistry of that carbon has not changed. That is kind of convenient. All right, we can use that to our advantage. All right, and then here is there's the pyridinium, which is the conjugate acid of pyridine. So substitution and elimination with the tosylates. So the alkyl tosylates are really good leaving groups, as we've mentioned. So the tosylates make for great leaving groups. They behave a lot like the alkyl halides. So it's approximately as good of a leaving group as maybe chloride, almost a bromide. All right, so you can do SN2 reactions and E2 reactions. Now, typically, we don't try to do this with like E1 and SN1. We try to stick with reactions yeah, we try to stick with the reactions that are E2 and SN2 because we have more control over those. So we'll see that they're most often used in that case, just like we would use a halide in an SN1 or halide in an halide in SN2 or a halide in an E2. We can use that like that here. So here we do the SN2 and we can form this ether, or if we use a strong sterically hindered base like potassium tert-butoxide, then we could do elimination. Okay, so now for inversion of stereochemistry, so inversion of the tosylates. We know that we retain the chemistry, the stereochemistry, when we form the tosylate, but when we do substitution, that substitution will occur by an SN2 mechanism, meaning that we'll get inversion of that stereogenic center that we started with. So here, if we've got a tosylate, this is a secondary tosylate. So we've got two alkyl groups on this carbon. In comes this cyanide ion. We get inversion of the stereochemistry, the configuration at that carbon, and then tosylate, and tosylate leaves. All right, so we get inversion when we do the SN2, just like we always do. But that gives us some interesting options here. So overall inversion of the stereochemistry is looks like this. So here we could take this cis alcohol. So we've got the methyl cyclohexanol here. We can form the tosylate. Remember, we retain the stereochemistry when we form that tosylate. And then we can use this methoxide to come in, and we'll get inversion of the stereochemistry when we do the SN2 reaction on that tosylate. And so here we will get the trans product. So overall, we'll end up with an inversion of the configuration. So that gives you the trans of that. If you wanted to get the cis of this, so let's say you wanted the cis version of this molecule instead of the trans version. Well, what we could do to get the cis version is reactions that we know. So starting with this alcohol, OH, all right, so the same starting material, but in our first step, we can use sodium hydride. That would deprotonate this and make an alkoxide. And then in our second step, we could do something like CH3Br, so methyl bromide. And then that would give us OCH3. So that would give us the cis compound. So again, going back and forth, so here this gives us cis by doing these two reactions. This gives us trans. So that gives us a little bit of a handle on how to control our stereochemistry. And I'm showing you this because that's cool. That's a cool thing to be able to control. Okay, so now we want to just to look at all the reactions and eliminations and substitutions that we can do. This is sort of a summary of all the things that we've talked about in the last couple of sections. Sulfuric acid or the POCl3 and pyridine will give us elimination reactions. We've got different options for substitution, so we can form the alkyl halides, and then with that alkyl halide we can use a nucleophile, or we could do the toluene sulfonyl chloride and form that, and then do substitution. And if we do inversion, we will end up getting the original stereochemistry back. If we do retention and inversion, we will get a different stereochemistry. So there's some cool things that we can do there. Let's look at parts C and D. Switch back over here. So here are parts C and D. All right, so the thionyl chloride plus pyridine, that is going to turn this into a chloride, but because it does it by by SN2, we're going to get inversion. So we will get the hydrogen coming forward and the chloride going back as our halide. All right, on this one, forming the toluene sulfonyl chloride gives us retention. I'm going to draw an intermediate product here. 1, 2, 3, 4, 5, 6. So O, TS, hydrogen. So we don't do an inversion when we form that, and then when we react that with the potassium iodide, we can get inversion on that SN2 reaction. And so here, hydrogen will come forward and our iodide will go back. That means that we do have a way to form iodide with inversion, much like what we did with the thionyl chloride and the phosphorus tribromide. Okay. So reactions of ethers with strong acids. So reactions of ethers with strong acids. So we know that alkoxides are not good leaving groups. So alkoxides are not good leaving groups. But if we react an ether with an acid, we'll create an alcohol, which is a pretty good leaving group. So that means that we can take a mineral acid like HBr or HI and cleave an ether into 2 alkyl halides. So we'll find that, so here is sort of the generic reaction. It can be symmetrical or it can be unsymmetrical. But you have to choose HBr or HI. We'll find this does not really work with HCl because of chloride just not being as good of a nucleophile as the bromide and the iodide. That said, we need 2 equivalents of our HBr and our HI, and we will get the alkyl halide of both sides plus water as our products. Okay, so here is an unsymmetrical ether reacted with 2 equivalents of HBr. So we'll get the cyclohexyl bromide and we'll get the ethyl bromide and then water. Here we have, say, tert-butyl methyl ether. That tert-butyl methyl will get the tert-butyl iodide and we'll get the methyl iodide as well, and water. The mechanism of this is really interesting. The mechanism is going to depend on the identity of the alkyl group. And in fact, we can have 2 different mechanisms in the same cleaving reaction. So the mechanism of the ether cleavage will depend on the structure of the alkyl group on the ether. All right, so you'll notice on this one, the tert-butyl methyl ether. Here on that tert-butyl, this is a tertiary carbon, and on this one, this is a primary, or no, this is a methyl carbon, not even primary. So on the tertiary carbon, we're that part of the cleavage where we break this bond, that's going to occur using an SN1 mechanism. This side, where we break the bond between oxygen and methyl, can't occur by SN1 because we can't form a methyl carbocation, at least not under normal conditions. So that one has to happen by an SN2 mechanism. So secondary and tertiary are all going to occur by SN1 mechanism when we break that bond. So we'll get carbocation intermediates. And methyl and primary are going to occur by an SN2 mechanism. All right, so here is the tert-butyl methyl ether, and we're going to go through the entire mechanism. All right, so when you have a choice, so you've got one that's going to go SN1 and one that's going to go SN2, the SN1 reaction will occur faster, so it's going to go first. So our first thing is we'll protonate the oxygen. If you're ever just not sure, start by protonating stuff, and that's going to get you in good position. So you'll protonate the oxygen, and that forms a good leaving group. So now the methanol can leave as a leaving group. We're going to use this in a little bit, so don't throw it away, right? So we're going to break this carbon-oxygen bond, and we'll form a carbocation. And then once that carbocation is formed, iodide will come in and react with the carbocation to give us the tert-butyl iodide. So cleavage of the bond gives us the tertiary carbocation, and then third, our iodide comes in and reacts with the carbocation. This second step is the rate determining step here. First step, protonation, is never rate determining, but breaking the bond is our rate determining step here. This third step is really fast. All right, now for the other part of the cleavage, we're going to take the methanol and react it with HI. So this is a slower reaction. SN2 reactions generally are slower than SN1 reactions. So we'll protonate as our first step of this part. All right, so we'll protonate. And then we're going to simultaneously break the bond between carbon and oxygen and make the bond between carbon and halogen. And of course, in this case, the halogen is the iodide. So we're going to look at number 64 and go through one of these mechanisms. And I find this a useful thing to do. And I usually end up putting one of these on the exam. So let's look at this. So we're going to do a stepwise detailed mechanism for this reaction. So first things first, if you're ever not sure, this one is almost the same as the last thing, except we have ethyl here instead of methyl. So if you're ever not sure where to start with protonating. So start with protonating. So we'll take the HBr. We're going to protonate that oxygen. All right, and that will give us this. And will give us this. Well, then this is a good leaving group. So we'll break the bond between carbon and oxygen. And that's going to give us a tertiary carbocation plus, let's see, here we had plus bromide. So tertiary carbocation plus this ethanol, which is that. And we're going to use that in the next step. And then finally, we're going to react this bromide with that tertiary carbocation. So we'll draw an arrow from the bromide to the tertiary carbocation, and that will give us that tertiary alkyl halide. So next, we want to take this alcohol, so I'm going to rewrite it. Again, in our first step, we're going to protonate the alcohol. I'm going to go ahead and draw some electrons here, so we know there's lone pairs of electrons there. So we'll protonate that alcohol, and then after we protonate that alcohol, and will give us this H2O plus. Now we can't break this and just form a carbocation because primary carbocations are no good. You can't do that. So instead, we're going to take the bromide that we just formed, and we're going to do a simultaneous reaction between that bromide and the carbon. So we'll make a new bond between carbon and bromine and break the bond between carbon and oxygen. And then that's going to give us the bromoethane plus H2O. And that is our detailed mechanism of this reaction. All right, well, that is a good place to stop for this video. We are at 40 minutes for this video, so I'm going to stop that. And in our next section, Chapter 9, Section 15, we're going to be looking at sulfur-containing compounds.